Logarithmic function, part 4. In this video, I would like to introduce some application of logarithm. How can we apply logarithm in our daily life? The first application, which is related to how to change the exponential functions to a linear form. In the last topic, we have already discussed some of our daily life example, which is in exponential form. For example, if you inverse a principal to a bank and the amount is in the exponential form and some depreciation rate or some growth rate also in exponential form. Here is one of the example. For example, the growth rate of a disease, H1N1. This is the relationship between the total number of bacteria. A is the initial numbers of bacteria and R is the growth rate. You can see this is an exponential form. Sometimes we cannot easy to do the prediction because if this is exponential function, the graph will grow sharply. So what can we do? We will try to plot a graph log n against t. Let's see how can we convert it. Okay. First of all, I want to find the values of log n. Okay, I want to add one new table. This is log n. By using your calculator, not very difficult to find the values, which is equal to 4.2, 4.4, 4.6, 4.8, and 5. Okay, if we plot the graph log n against t, here is a straight line when you plot this 5 point. And maybe the scientists also want to know the initial numbers. But if I see this pattern, it is quite difficult to see the initial number of bacteria. So you can extend it. So I know the y-intercept is equal to 3.8. And then we can also find the slope of this graph. Maybe you will ask why the exponential function can plot a straight line. Okay, we can. I want to explain it detailedly. The original function is n is equal to a times 1 plus r to the power of t. If we take log on both sides with base 10, log n is equal to log a times 1 plus r to the power t. Log a times log b, we can separate them as log a plus log b. And then this power, we can put it in front of the log function. You can see at the original, the x coordinates in the interposition so that the graph is exponential function. But after applying the logarithmic function on both sides, you can see the unknown, okay? The independent variable. From the index position, we can put it in front of the log function. So this is a linear function. According to this form, you can see this is our new y-axis, and it's equal to something plus x time another constant, maybe you can call it d. Can you recognize this as y is equal to mx plus c? So I know the y-intercept is equal to log a and the slope is equal to log 1 plus r. Let's see how to find the values of a and r. That means the initial number of bacteria and the growth rate. Because y-intercept is equal to 3.8, so 3.8 is equal to log a. I know a is equal to 10 to the power 3.8. This is the original number of bacteria 2 hours before. How about slope? The slope is equal to, maybe you can use the slope, the formula of the slope is 5 minus 3.8 over 6 minus 0. I use this two coordinate. This coordinate is 6 and 5. And the second coordinate is 0 and 3.8. So we can find the values of slope. So the answer is 0.2. 0.2 is equal to log 1 plus r. Then 1 plus r is equal to 10 to the power 0.2. You can find the values of r. R is equal to 0.585. So remember, we can make good use of log function, the property of the log function. We can change the exponential function to a linear function. But the main point is that after changing to the linear equations, how can we relate the y-intercept and the slope to the original constant? Let's see another example. For example, 12. Given the graph, Pi asks you to find the y-intercept and the slope. If the original relationship between y and x is in this form, how can we make good use of the y-intercept and slope? Find the constant unknown k and n. Okay, and maybe you can pause the video and check the answer later. Okay, let's check the answer together. Part A. I want to find the y-intercept. Maybe your answer is 1. But if I were you, I will write down 1.0. Because the information from the graph is not exact value, it's approximate value. So I will use 1.0 rather than 1. How about slope? Maybe you can choose two coordinates. For example, this one is 0 and 1. And then this point is 3.5 and 8. So apply the formula. 8 minus 1 is equal to 3.5 minus 0. So the answer is 2. Maybe the answer is 2.0 is okay because this is approximate values. This point is not exactly, the y-coordinate of this point is not exactly equal to 8. Okay, maybe it's 8.0 and this is 1.0 and so on. Part B. I know the original relationship between x and y is y is equal to k times x to the power n. This is log y and log x. How can we convert this form to a linear form? Take log on both sides. Log y is equal to log, do it step by step, log k times x to the power n. And then apply the property log a times b is equal to log a plus log b, and then plus n log x log y. Can you see the y-axis is log y, and this is log y, this is y. How about x? X-axis is log x, and this is log x. So this is in the form of y, the whole term, is equal to mx plus c. So I know n is equal to the slope of the straight line. So n is equal to 2.0. And log k is equal to the y-intercept. So 1.0 is equal to log k. So k is equal to 10 to the power 1.0 is equal to 10. This is the first example, first application of logarithmic function. We can change exponential function to a linear form. Second application. The second application is related to the definition of the basic law. For example, log 9830. Can you guess what's the values of this term without using calculator? Sometimes I will use this meaning of log. I know the answer must be 3 point something. Maybe 3.9 something. Why I'm sure the value is equal to 3 point something? Because one of the meaning of log is we are trying to count the power of 10. Okay, if this term is 9830, then I know this is nearly to 10 to the power 4, because this is 10,000. So one of the meaning of log is we are trying to count the number of digits. Okay, similar to this meaning. So how can we make good use of this meaning? In our daily life, sometimes the values of the variable is very large or very small. Then we can make good use of this meaning of log. We try to scale down or scale up that values because that value is very small or very large. I want to use this example, these two examples. The first one is the nullness of sound. The nullness of sound, which is related to the sound intensity. But the sound intensity in general, okay, is very small. For example, is 10 to the power negative 13 watt per meter square. The value is very small. But if I tell you, the sound intensity is around 10 to the power negative 9 watt per meter square, maybe you will consider, okay, the sound is very small. Then I will not affect by that sound intensity. But you know that sound intensity, if we convert to another unit, which is called decibel, which is very large, that means we are affected by that small sound intensity. So let's see one of the formula. Decibel is the unit of for measuring the loudness of sound. This is the definition of the decibel. This L. L is equal to 10 times log. This L is the sound intensity we received. We received it. How about over I log? This is the minimum audible sound intensity. That means it's the if we can hear if the sound intensity is equal to 10 to the power negative 12. So let's see. If one person make noise of 80 decibel, okay, what's the meaning of 80 decibel? Okay, let's try to calculate what's the sound level, okay, or sound intensity if the decibel is 80. So make good use of the formula. So because the decibel is equal to 80, 80 is equal to 10 by using the above formula, 10 times log L over 10 to the power negative 12, the minimum audible sound, and then divide 10 on both sides and make good use of the meaning, the definition of log. So it's 10 to the power 8 is equal to L over 10 to the power negative 12 times 10 to the power negative 12 on both sides. So the final answer, the sound intensity is 10 to the power negative 4 watt per meter square. Maybe the sound intensity is small. It's very small because 10 to the power negative 4 maybe 0.0001. But do you know 80 decibel is not quite small. How about another? Okay, make noise of 100 decibel. Let's see the sound intensity of 100 decibel. Because I have two unknown, okay, the first one is L and we have two sound intensity. I let L 100 be the sound intensity of 100 decibel. And I make good use of the formula. You can see L 100 is equal to 10 to the power negative 2 watt per meter square. The sound intensity is quite small, but do you remember? Okay, 100 decibel is not quite small. And find the ratio of the sound intensity by two persons. So the Record the answer. Is equal to 10 to the power negative 4 over 10 to the power negative 2. The answer is 100 to 1. Okay, maybe you can do for exercise 13 and we can check the answer in our lesson. I want to illustrate another example how to make good use of log in our daily life. Same idea. Sometimes we'll use a log in the earthquake to measure the scale. Why? Because how to measure the earthquake to describe the, we'll use Richter scale. Why we need to use log? Because if we want to measure the earthquake, we need to measure the power to see what's the power of that earthquake. But do you know that power is quite large? So we want to scale down. We just want to count the number of digits of the energy, so that we can use log to try to scale down the energy, and then to see how's the series of the earthquake. So this is the formula. Log E is equal to 4.8 plus 1.5 R. Log E is equal to 4.8 plus 1.5 R. E is stand for the energy. R is stand for the Richter scale. You can see in 2008, the earthquake, the scale is 6.7 in the mainland China. I want to calculate the energy released by this earthquake. Okay, use the formula. Log E is equal to 4.8 plus 1.5 times 6.7. Then, by solving these equations, you can see log E is equal to 4.8 plus 1.5 times 6.7. 4.5 plus 1.5 times 6.7 is equal to 14.85. So E is equal to 10 to the power 14.85. That means which is equal to 7.08 times 10 to the power 14 joule energy. You can see that earthquake release huge number of energy. If we use this energy, sometimes it is very difficult to compare by different earthquake. But by using the log function, we can scale down it and then easy to compare with different earthquake. This is a second daily life example. Remember, you do not need to remember this formula. In public exam, if we need to know or we need to use the formula, it will give the formula to you, and you can apply that formula rather than this formula.